When we tweak a photograph in editing software, boosting contrast or lifting shadows to make it look better, we are engaging in image enhancement. This process is fundamentally subjective, guided by aesthetic preference rather than data integrity. Image restoration operates as a rigorous inverse problem. The objective is to mathematically recover the original, pristine data from a corrupted state, moving beyond simple visual appeal to solve for a specific ground truth. This relationship is defined by a central equation that governs how images degrade. In this model, G represents the noisy image we observe, F is the uncorrupted original signal we want to find, and eta is the specific noise term that has contaminated our data. A common error is attempting to fix this by simply blurring the image. This approach treats noise as a generic problem, but it fails to solve the equation, often destroying the very data we want to save. Scientific recovery requires us to profile the noise term with high precision. Only by identifying the exact signature of the interference can we engineer a countermeasure that restores the underlying signal. Without identifying the precise mathematical signature of the corruption, we cannot distinguish the noise from the original signal, leaving the underlying data unrecoverable. Digital interference follows specific statistical distributions determined by the physics of the imaging sensor. These patterns allow us to model noise through a probability density function, or PDF. These plots are statistical fingerprints of different interference types. A Gaussian distribution models predictable electrical noise from sensor heat. In contrast, impulse noise creates extreme isolated spikes, modeling salt and pepper corruption, where pixels short to pure black or white. To find out which type of noise is attacking an image, we analyze its histogram, a data map showing the frequency of every pixel value in the frame. We can use this basic test pattern to establish what a clean, uncorrupted baseline looks like in a histogram. When we add Gaussian noise, the histogram peaks begin to spread into bell shapes, reflecting the normally distributed variance added to the pixels. Other interference types, like Rayleigh and gamma noise, produce their own distinct skews and asymmetries in the histogram. Impulse noise is identified by these two sharp, isolated lines at the absolute edges of the histogram, representing the black and white spikes of the salt and pepper effect. Identifying this histogram signature is the first step in restoration. Choosing a filter that doesn't match the noise profile will lead to total data loss. Within the spatial domain, the most basic countermeasure is the Arithmetic Mean filter, which uses a convolution mask to process the image. A 3x3 grid slides across the pixel matrix, replacing the center pixel with the average of its neighbors. While this smooths out Gaussian noise, it destroys high-frequency data. Because edges are sharp pixel transitions, the averaging process blurs these boundaries, softening the image. The geometric mean filter offers a sophisticated alternative. Instead of summing, it calculates the product of the window's pixels and takes the nth root. Multiplying the values allows the filter to suppress extreme noise spikes while exerting less pressure on surrounding structural data. We can see the difference in performance by applying both filters to a highly detailed subject. This X-ray circuit board is degraded by Gaussian noise, obscuring its pathways. The arithmetic mean in panel C produces a muddy result where fine lines merge. The geometric mean in panel D suppresses the noise while maintaining much sharper, more accurate structural edges. In the context of restoration, simple blurring is too imprecise. Effective data recovery requires operators that respect the geometry of the original signal. Some images face asymmetric corruption, where only dark pepper spots or bright salt spikes attack the frame. The Contraharmonic mean filter uses a control variable, Q, to target this noise. Here, we see pepper noise removed by setting Q to positive 1.5. A positive Q value acts as the mathematical inverse for dark spikes, replacing those pepper spots with surrounding intensity levels. If the image is instead corrupted by bright salt noise, the filter requires a negative Q value to achieve the same result. This specialization makes the algorithm dangerous. If an engineer misinterprets the noise profile and applies the wrong algebraic sign for Q, the result is a total system failure. This is what happens when a negative Q value is applied to pepper noise. The mismatched algorithm does more than just fail. It mathematically amplifies the entropy of the system, actively destroying the dataset rather than cleaning it. Applying a restoration filter without an accurate profile of the underlying noise is a direct threat to the data. Periodic electromagnetic interference creates patterns that spatial filters cannot easily address. In this lunar landscape, the interference appears as a repeating sinusoidal wave, creating a global pattern of webbing that covers the entire image. Spatial masks only look at local clusters of pixels, making them blind to these repeating global waves. To fix this, we use a Fourier transform to move from the spatial domain into the frequency domain. This shift reveals the frequency spectrum. The sprawling pattern of noise is now condensed into these bright, isolated points of light, separated from the actual image data. We can now apply a Butterworth band reject filter, which is designed to surgically remove specific frequencies. The filter acts as a mask, zeroing out the precise coordinates where the noise stars appear, while leaving the rest of the spectrum intact. When transformed back to spatial coordinates, the global interference is gone, revealing the pristine details underneath. By leaving the physical dimensions of the image and operating on a mathematical plane, we can isolate and remove global interference without altering the image structure. The primary limitation of static filters is that they apply the same mathematical rules to every pixel, regardless of its local context. The adaptive median filter addresses this by replacing fixed operations with dynamic spatial awareness. Instead of using a fixed grid, this algorithm resizes its search window in real time. If it detects a cluster of noise, it expands its view until it finds clean, reliable data to use for its calculation. It uses a logic gate called level A to determine if the local median itself is a noise spike. If it is, the filter expands the boundary box until a valid median is found. A second gate, level B, then determines if the target pixel is truly corrupt. If it recognizes a valid edge or detail, the algorithm leaves the pixel untouched, preserving the original data. This dynamic logic allows the filter to simultaneously clear dense noise spikes and smooth out background variance, while perfectly protecting sharp structural edges. From deep space orbital imagery to industrial scans, the most effective methods of data recovery rely on precise statistical modeling. Digital image restoration proves that entropy can be reversed only when we move past superficial enhancement and engineer an exact